are going to do is that a lot of people don't know what is quantum computing at all, in general. We are specialists and so on. For us, it's common. So I will ask, one of you to mention what quantum computing is in general. Then we are going to talk about what stage it is in now in terms of deployment or what's all happening, what are the different physics, etc. Mention but not get into details, because I don't think the audience will be able to get into understanding of the physics in detail. And then we talk a lot more into future of quantum computing overall, which you can include quantum communications and quantum cryptography, of whatever is happening, whatever is potential. And then another topic I want to talk about is there any acquisition opportunities that may happen? I'm not saying it will be, right? Roll up. So consolidations, exits into going public, etc. Right? Is the future one. Any future thing that's being planned, we can talk about it. And very quick introduction, one or two liners. Please start, Dr. Spike Narayan.
Hi, I'm Spike Narayan. I'm the executive director for an NSF organization called Engineering Research Visioning Alliance. Before this, I was at IBM. I used to run the San Jose Research Lab in California.
Okay, thank you. Dr. Priyadarshini?
Yeah, I'm Dr. Satyam Priyadarshi. I did my PhD long time back in quantum mechanics and spent last couple of years in energy and other industries, and now a visiting professor at Virginia Tech and IIT Bombay, and do consulting in quantum technologies.
Okay, thank you. Prakash Ramachandran?
Yeah, good morning, all to everyone. I am Prakash Ramachandran. I am a IIT Bombay graduate of 80. Currently, I am the Quantum Information Technology QIT IEEE working group chair, and have a foundation called Emerging Open Tech Foundation in India out of Mumbai, where we do work on the quantum, semiconductor, as well as on the AI. These are the three areas I focus on.
Let me clarify for people, audience who may not know, all of you may be familiar. IEEE has forward-looking teams, 10-year, normally 2021 to 2030, for example. Now, I've been there for four or 5 decades in my own life. And under that, even though we could be in multiple domains, and Prakash Ramachandran and Dr. Chintan Oza, both are there in the forward-looking on the quantum computing relevant to our topic. There are other things also they do. Dr. Chintan Oza.
Thank you so much, sir.
Yeah.
Thank you so much, sir. Pleasure being here. This is Chintan Oza, based out of India. I am co-founder of Quantum Information Technology Work Group within IEEE INGR. We want to standardize the roadmap and bring all experts together so that we can build a roadmap which is more informative. Apart from this, I own a company called Anantam Ecosystem, do a lot of consulting with startups, bit of government advisory in Startup 20 and G20. Also connected with various other professional organizations like PMI, Bombay Management Association, etc.
Thank you.
I have authored 5 books. 4 of them are part of the World Bank project.
We'll talk more only on quantum computing, because
thank you.
Now I've been given request to make it all discussion only. You're going and coming back, Dr. Chintan Oza. Yeah. Okay. Now, what is quantum computing? Let me start again with Dr. Spike Narayan. Make it easy for people who may not know, and also for people who may also know some physics.
Sure. Okay. So I want to kind of give you a perspective of where quantum computing is relative to semiconductor standard computing that all of us are very familiar with, just to give you a level set as to the infancy of the whole topic, right? So you'll appreciate that. So if you go back to 1970, one of the pioneers of the whole concept of quantum information theory was actually proposed by Charlie Bennett, who wrote these words, quantum information theory, in his actually lab notebook in 1970. And it took more than 10 years after that for Richard Feynman and his colleagues, who are actually considered pioneers in quantum computing, who used mathematics and theoretical quantum mechanics to advance the field in the 80s. So it took 10 years from the concept of what is quantum information theory, which is basically quantum computing genesis, to actually having some good theoretical methodologies to understand what it is, right? So theoretical quantum mechanics and mathematics were used to kind of generate it. But it became very apparent very quickly that while quantum mechanics offers a rich computational model, they actually need to build a quantum computer, and that's how the quest began. So in the late 90s, that's when the first 2-qubit quantum computer actually became available, and that was the beginning of the transformation from theory into reality. So fast forward to 2025, a lot of work has gone on in trying to understand how to scale beyond 2 qubits. And this is where the real challenge is, and we talk about it in terms of future as we get into the panel discussion down the road. But I think, let me just put one provocative statement in there, and that is, in this decade, which meaning we have about 5 to 6 years left, it is entirely likely and mostly possible that quantum and classical computing working together, not by itself, working together, will outperform classical computing used alone. And I think that is kind of the benchmark that we need to think about. It is not a technology that is going to replace conventional computing or classical computing, but it's going to be working in tandem with classical computing, and it'll outperform classical computing before the end of this decade. That, I think some people call that quantum advantage. So why is it such a challenge, right? I mean, if you look at the semiconductor industry, we had Moore's law and we were marching along and we made incredible progress in the number of transistors in a chip and so on, right? But quantum computing is a little different in that they have some very weird physics in it. Things you would have heard words like interference and entanglement and superposition and all of these. These are what makes classical computers, to simulate classical computers at scale, very, very hard, right? So because of all these weird physics that goes on here, and the fact that quantum computing is actually an exponential power representation, there are lots of engineering challenges, which is, I think, what is going to drive what the work is going on in the next decade or so, right? To put it in perspective, right, if you look at how many classical bits are needed to represent entangled qubits, and this is how one would say that we can simulate a quantum computer on a classical computer, but I'll show you why that is very quickly reaching its limits, right? So if you look at trying to represent quantum entangled qubits, it takes 512 classical bits to represent just 2-qubit system. 512 just to represent 2. If you go to a 3-qubit system, it'll take you 1024 bits. And you can start to appreciate what's happening in this exponential behavior.
2 to the power of n rule.
2 to the power n. And by the time you get to 35 qubits, you need 550 gigabytes in terms of classical bits to simulate it. And if you want to just do a mere 100-qubit system simulation, there are not enough atoms in the entire planet to do it. So you'll understand why very quickly to go from a 2-qubit computer to a 100-qubit computer, you simply cannot simulate it on a classical computer. And this is where the real challenge is. And that's why it is so important for everybody to kind of think about the engineering challenges, and we can talk more as we go along. But in the latter part of this decade, I would say what you will see happening is how AI, quantum computing, and classical computing are going to work together to advance accelerated experimentation and discovery. And this is where the real money is going to be made, is accelerated experiment and discovery, whether it's in the pharma field, whether it's in other materials fields, is the real first impact you will see of quantum computing. And it's the all three of these coming together in very interesting ways. And I think other people in this panel, I'm sure, will have some interesting perspectives on that. Thank you.
Thank you. Dr. Priyadarshi, what I want to hear from you and explain to us, that on the topic of you cannot do quantum computing in the way that Dr. Spike Narayana mentioned, at room temperature at all, because at room temperature, there's a lot of chaos. You have to go down to helium temperature. Take it from there and explain more of why low temperature is a very important thing at helium and more. Yeah.
No, I think the best way to think about is the analogy of our traditional computers, right? I think all of us probably remember when the regular computers came, and even since there are some people from IIT Bombay, they would remember when IIT Bombay or TIFR got their computers, it was kept in such a cold air conditioned room and dust proof, no shoes allowed, right? So because the boxes were so large and they were generating so much heat. So if you think of it like where we are today, we carry the same power in a phone and we take it to any temperature, right? So if you think of it from the same principles, right, when we are building this technology, by the time we realize we go to say 100 qubits or something, we will be generating huge amount of heat in the process, whether we are using lasers or whether we are doing photonics, neutral atom, or ion trap, whichever method, whichever the modalities. There are 6 or 7 modalities people are working now, and even semiconductor is one of them. All of them have its own challenges, and hence refrigeration or the cooling part is critical for them, right? And there are few companies which are maybe I would call ahead of the game in trying to control that and thinking of building a system which is modular. And I was very impressed with the way they have started thinking, which looks like already we would call it 2025 for traditional computer. They are actually ahead of it in the quantum sense. So I think there are in order to really do meaningful calculations, this is it's not about just the qubits, right? It is also how much calculations we are doing, compute power, the energy itself that we will be using, and this energy usage, compute needed, and the actual hardware, the way it is configured, the configuration of the system. These three will require significant amount of cooling effect, and that I think people understand it well now. It's a question of miniaturizing and making it transportable, if you want to call it, or ready for a quantum data center.
Okay, thank you. And I'll request someone else to, I know you can all answer the same question. Dr. Chintanoza, Dr. Priyadashi mentioned different device physics, ion trap, etc., etc. Can you enumerate and pick up one or two, and then I'll request other people to go into other ones examples, because people don't know quantum means only one device, one type generally. Those who don't know, please go ahead.
Yeah, so there are several types of quantum technologies people have been experimenting, and uh, uh, but however, if you look at the usability as far as the business case is concerned, I mean, because this is where I look at quantum computers, right, from the business case or towards the marketing side of it or scaling it further, then the cost of each technology varies, and then that is where at times it becomes really difficult to establish the role of quantum computing in building certain use case. I mean, if we look at financial risk modeling, then definitely we can implement couple of technologies, but not all technologies are mature. Even the ecosystem is not that mature that we can actually build all sort of use cases on various types of technologies which are available around us right now. So that is something which I feel it is going to mature with over period of time. But as far as business case is concerned, as far as usability is concerned, as far as maturity of the technology and ecosystem is concerned, then the use case, as in when we build any use case, these aspects really drive the success of the use case.
Thank you. Prakash, I'll come back to you. I want to go back to Dr. Spike Narayan. Could you say a little more on the different device technologies, including not only that, but also the Josephson junction, etc., so that people understand it's not one, there are multiple, any quick understanding of for the people. What you are?
Yeah. So I think Chintan already kind of referred to some of the technologies, but I think there are some broad categories, I would say, of technologies. Those that are somewhat silicon based, and I would say Josephson junction is also silicon based, as also silicon quantum dot technology that's used on silicon is also silicon based, and some of the others are not, like ion traps and a few other technologies there are somewhat different.
Even the photon being made into two and all of that.
There's lots of technologies, but I think the key thing to remember is while there are a handful, maybe a dozen or so different ideas or scientific ways in which you can actually do quantum computing, now we have to think that for it to be actually relevant in terms of being able to solve problems at scale, I'm not talking about toy problems. We need to go to technologies that have some ability to scale fast. And I think this is where the challenge is today. Is there are lots of 3 or 4 competing technologies, and who's to say what's better? We don't know yet. But the real advances in quantum computing will actually happen when quantum computing providers have partnerships with industry that actually jumps into this whole area early. So the visionary industries that can partner with quantum computing providers, that is where things start to scale. Till that happens, if it's just people in universities dabbling or even in industrial labs dabbling, you're not going to get a whole lot of work on scaling, and that is at the core of everything. And that happens only when somebody who needs a quantum computer and somebody who has a quantum computer come together, and then the whole effort on scaling will start to happen, and that's where the engineering research will start to happen. So while there are many different technologies, I think we just need to keep our eyes on those that are starting to show promise of scaling. From what we know today, the one based on Josephson junction, which Google does and which IBM does, 2 of the many that do, they have at least years of experimenting with this, and they're already putting out systems that have lots and lots of qubits, in spite of all the challenges of noise and everything that Dr. Priyadarshini mentioned. And there are others that are not really necessarily doing it at scale. There are still toy problems being solved, and those are all good. It just remains to be seen which one actually scales. And I think we don't know the answer to that yet.
Okay, very good. You covered it very quickly, and I'm going to come back to that unless anyone wants to jump and mention anything more. Okay, Prakash.
Sure.
Let's talk about applications. What are the applications in IEEE, and you yourselves and Dr. Chintan Oza are looking at what could be used in the next 5 years to 10 years?
So put it 5 years to 10 years is a little long time frame to predict with the amount of changes, day-to-day changes. It is, I would say 3 years is a safer bet than 5-year prediction. But I would still guess that, as Dr. Spike mentioned, definitely the what you call the superconducting quantum SCQ, what we call, which is at the 0 degree Kelvin, I would say, which is at the negative minus 273 degree plus you can add 20, so around minus 300 degree you can say centigrade. At that level, we are able to produce qubits, lattices, and grids or arrays, and that is in the range of, for the IBM, it is in the range of thousands, at least 1,024,000 types. Google did around 250, and Rigetti has come around 54. So the 3 transpond players in the industry are the IBM, the Google, and the Rigetti. These 3 are the prominent ones, and they have got what you call a good coherence, good, they call it as T1 and T2, which is the amplitude and phase timings, which are in the range of T1, T2, somewhere in the 50 nanoseconds types. So given that, within that, you have to concurrently execute several threads. I would say they are the top ones at this time, maturity level. Second one, obviously, you have the So there is one with electron, one with photon. Photons are always going to be weightless, and those are the ones which are photonic chips, one of the them. And then there is at room temperature, like you have got NV, nitrogen vacancy, which is based on diamond. And then there are ion trap, which is ion trap is very good. However, they were tested by US defense, and they claimed that the delays or repeatability is a little bit of a challenge for them. They are in the millisecond range, which is hundreds of milliseconds, which is difficult for them to absorb. So given that, I see that superconducting quantum is going to be the transmon players are going to be the top ones. They do have a problem. Everybody has some problem or the other. Down the you have the stack, entire stack. You can start with the hardware layer, then analog, which is, and then you can go with the control layer where you try to control these pulses and all to be able to do the mixed signal and all that, whatever the tuning and all that which you do using the microwave, the resonance and all. So those are other challenges, and obviously the at the higher level you have got the standard, at least two of them, growers and search algorithm, and you have got the what you call the prime number factoring of shows. These are the two algorithms which, even if you go down the technology which is gate based, there are two obviously. One is gate based, other is the annealers, or what we call as adiabatic computing. Adiabatic is more prominently used in US in all the national laboratories, because the one which was around 2010, Davos brought it in, and that is the one which is more more being utilized because the investment has been there, and a lot of uh, government organizations are using it. However, gate-based computing, that is the one which is going to be portable, which is going to will allow scaling, as well as it has got the ability to reduce the error quantum, like Willow, currently greatest one, which came just even December in from Google, really changed the whole thing. So the integrated circuit SQUID, what we call, that is superconducting quantum integrated device, SQUID is the one which we see as the one which will prominently drive the industry at least for a year or two. That's the expectation. Trying to predict beyond 3 years is hard, but I would say Y2Q, which is year to quantum, could be 27 or 28, depending on mandates enforced by the various national governments to overcome the cryptography breakthrough, which will happen the day quantum becomes real. So these
Thank
are
you.
my some of the inputs, but I would not be willing to bet for 5 years. 3 years
Okay.
is good enough,
Okay.
I would say.
Okay. Now I will talk about betting and all that a little later. When I
Mhm.
have lots of things that I just want you guys to answer. I'm not answering any questions, but bringing
Mhm.
only the questions intentionally. When you mentioned minus 273, those who are in the audience who are physics savvy at the depth, when the closer you go to minus 273 or 0 degrees Kelvin, Bose-Einstein condensate will form, and then it's so difficult to differentiate between what is what, where is what. And that may not be ideal, and no one has even talked about using that for quantum computing. Just to mention, no discussion for now. Now that we talked about, you want to say anything? No, okay. What I want to talk about is future, lot more future now, immediately. What I want to look at is that lots of money has been poured. I'm trying to bring the questions for you to answer and clarify. And Cambridge computing, quantum computing was, I think even IBM put $300 million right away. Please clarify if that's the range of numbers and so on. A lot of money has been poured, billions, and all companies, lots of money in the first round, right? It's not in the later rounds. And so, is there any of these who may not be able to cut the situation and get to a profitability stage early enough instead of asking more and more money? Is that anything that in the industry I'm talking about, any industry players you think that we have to be worried about, especially because Rigetti, I've seen, going public and prices and all that. In a day, they're talking lots of swings and so on, like that. Now let's talk about the valuation and application, customers, what kind of volatility is there. Dr. Priyadarshi, you can start, and Dr. The other people can go on that.
Yes, there has been significant amount of money put into quantum technologies,
Yeah.
And people can call it hype, but the actual total amount that has been put into quantum is not significant compared to what has been put into companies of
ChatGPT type.
right, exactly. Right. So I think this is where we have to look at the technology is also, as Dr. Spike was saying, we are still in early stages of maturing the technology, right? All the modalities are in the play. And when some news comes about a certain modality, suddenly people think, oh, this is the great modality we should really focus on. And investors are willing to go that route or this route, right? The recent dip in the market was because Nvidia person said something, and then suddenly everybody was thinking, and then 2 weeks later he's himself doing a quantum event. So these things are not really prediction of how the companies will behave. Yes, there is a certainly need for more money. I completely, having seen some of the manufacturing places of these quantum computers, I can tell you they require a lot more resources than what we think sitting outside in an air-conditioned office. Uh, if you just think of simple things, right? We only talk about quantum physicist, quantum chemist, quantum scientist, but people with mechanical engineering, the electrical engineering skills that are needed for quantum computers are are in demand, so to say. And these require new kind of like what you call tools to be developed, and those things require investment. People are ready to put money in big quantum computing company, but not ready to put it into the supporting system. So if supporting system, if you think of it, the quantum supply chain, I'm not talking about supply chain in that sense, but quantum computer supply chain, we need to invest in all those areas. So there is where I think you will see that people will start investing in it, especially I think there was last week there was news about this company called KIULTRA, I think that's the name. I could be wrong, but related to refrigeration, right? So suddenly now refrigeration is getting interesting, right? So companies are willing to put money for them. So I think this is early stage of investment. And currently, if you look at big companies that are supporting, I think you mentioned Cambridge Quantum, which got acquired by Honeywell, and now it's called Quantinium. But these companies like neutral atom companies and both ion trap companies are partnering with companies like Rolls-Royce, HSBC, and others. So there are well-known scientific business case, and modalities are being tested, or maybe call it very early proof of concept or proof of value being tested. So any of those things, and of course the financial industry has been, banks, at least 2 banks I know are working closely on some use cases with various people, but scale of problem, it still remains small. But the investment in another category, we forget that these computers require special software, and that requires investment. It's like, again, my analogy goes back to traditional computer. When we have regular computers, then we got parallel computers, then we got message passing, then we got right, threads and everything. Every software engineers evolve.
Computers,
right. Software engineers evolve. Same thing where here will quantum engineers will evolve with us, with the whichever modality goes ahead. But the foundational part still remains a challenge in terms of understanding how to write your code for qubits.
See, the issue that I also want to bring out is capital intensity. When you all understand, for the audience sake, capital intensity applies for how much money is available to be put into any industry in general It could be flash memory, to get to wherever it was, to wherever it is now. Capital intensity was a very important thing. And is that so much money available, not from the government agencies and experimental level, but also to create revenue growth, all of that, and you can use it everywhere in over time in the industry. Anything you think about, comment about capital intensity? If that is not there, the industry is going to suffocate over time. Any
Sir,
comment on capital
I
intensity?
can comment on that. The capex versus opex is always a challenge. And what we find that at least in 2022, the numbers were there. Quarter of the uh, investment have gone into what you call software side of the stack, whereas three-fourth went into devices and hardware. The reason is very simple because unless you have the devices available to actually do the computation, it is difficult. And it is very much like our 5G industry where we are the telecom industry where we went through, oh, we will do a standard architecture. No, no, we'll do a non-standard architecture. So similarly here, hybrid has to have a preference over that means HPC combined with quantum is going to be the first to be available for real utilization. So you will find that investing in GPU does not necessarily means it is not going to contribute to quantum because it will bring to HPC and the HPC eventually will be used by quantum. So you are going to see that investment and the ancillary industry, which we call HPC is ancillary to quantum, is really good, not bad. So it's not that quantum can steal everything. You will have to have the capex and opex and also hardware and software and middleware. So the distribution of it is very difficult. But one thing is very clear: use cases are being what you call tested. There are enough use cases which have been used on the finance side, especially on the trading and all, which is JP Morgan's here as well as in India, in some of the RBI's attempts. So I would say that yes, the split of the money is going to be in different categories. At the same time, AI will accelerate quantum, HPC will accelerate quantum, and quantum in itself has enough what you call pull up to be able to get to a level where people will start defending at national level. Public private partnership, PPP, is one of the key factors, and this is there in Europeans much higher than in other places, but definitely US is more on the industry side and India is more on the government side. So you are going to have different regions doing different areas. At the end of the day, there is no interoperability standard, as even Quasm 2.0, which is only meant for what you call the application usage of the API instruction set architectures like RISC-V, and Quasm 3.0, which is the heterogeneous, or a heterogeneous means classical as well as the quantum pure computation. That's the one which needs to evolve for us to be able to reach early, what you call delivery of industrial grade quantum computing.
Prakash, I'm going to go to more items to discuss. There's quite a lot to discuss. I use the word QCCC, quantum communications, quantum computing, communications, and cryptography. QC cubed also I use sometimes when I write it. So here, when it comes to capital intensity, because that's the key everywhere, and not enough money, even though you say it's not enough money that being put in over time for ubiquity of the QCCC, QC cubed, everywhere, like we have cell phones everywhere, computers everywhere, compared to when it started, right? And IBM architectures and all that, SNA, you already know, compared to where it is to progress, the amount of money that is required to manufacture, supply chain, quality control, components and total assembly and energy requirement. Trying to bring in variety of things, because even in data centers and even the chat GPT type, I'm saying the total energy requirement, electricity for cooling, 50% of the whole thing is cooling, and for the functioning is 50%, for example, approximately, is going to be an issue. So now what they're doing is, I'm trying to bring that into quantum computing also in the future. That's the point. In there, when you try to do all of this, the issue is of not being able to get enough cooling, enough energy, as you, Dr. Priyadashi, you mentioned. What are the issues there? Even though by the time SMR will be happening, that is small and medium nuclear reactors. So let's look at overall. Any comment, Dr. Chintan Oza? You didn't get to speak as much, so I want to equalize time if possible. Go ahead.
Yeah, thank you so much. I guess, in my view, there are two things which we need to think beyond the unlimited source of funding. First one
Yeah,
is standardization.
yeah,
The tech needs to be supported by standardization. Various standardizing agencies or
yeah,
associations needs to take effort in standardizing quantum systems. And second one is cross-border trade, because irrespective of unlimited money and standardization, if you're not able to sell beyond your border, then probably you are limiting the growth. And then this
yeah.
is where you are again pushing those silos and duplicating the investment, and that itself would serve as a hurdle to the adoption.
Yeah. Okay. Anyone else? Please jump in. I mean,
Yeah,
just give me the areas,
yeah,
please. Go
sure.
ahead.
I just want to mention this CapEx thing that you brought up, Murthy, because I think just to put things in perspective, the amount
I call it capital intensity, which is different from.
yes, right. So just to put it in perspective, in the semiconductor industry, we spend trillions of dollars. In
Yeah.
the quantum computing industry, it is hundreds of millions of dollars. So there are many, many zeros that are missing
That's
from,
right. We can do
and
it.
which is fine, which is because the technology is not mature, you're not going to get $1 trillion investment now. But the bottom line is what Dr. Priyadarshini said is the ecosystem around quantum is only now starting to kind of break loose, right? And that is a very, very key issue, because without the ecosystem in place, you're not going to get fast scaling at all, right? It can
Correct.
be done by one company. It cannot be done by an academic institution. It requires everybody coming together, including the national labs, venture capitalists. Everybody has to come together to create this ecosystem that will promote the rapid growth and scaling of quantum computing. And also, like he mentioned, only about, no, I would say 70 to 80% of the people needed to do the scaling and the ecosystem don't have to be physicists. They don't need to even understand what quantum physics is. It's hardcore engineering research that needs to be done at many, many levels to kind of get
Automation and all that.
not just automation, just understanding heat transfer.
Understanding first, yeah.
Basic things like that. How do you build something that is insulated? It is thermally insulating, but electrically conducting, right? So there are many, many challenges in quantum that standard engineering capabilities are required. And I think that is where the real challenge is. How quickly can we grow the infrastructure? And how quickly can we have the ecosystem players kind of become part of the mainstream work for quantum computing?
Okay. Anyone else want to jump?
Yeah, I would like to add here.
Yeah.
The dilution refrigerator, which is being used, which is a vacuum created inside a particular chamber, that being used, I think there are industrial uh, vacuum tubes available. And in sense of energy, because why do we do that? Is because we want the thermal noise to be low, to be able to discern. And this is at the what you call squid level or at the analog level. Now, if you go an intermediate, which is at the control system layer, the control system which is driving these qubits into swapping and whatever the other instructions are being used, that itself needs to be at millikelvin to operate it. And then on top of it, you can have the classical computer managing it. So overall energy, if you look at the data center, 40% usually goes into what you call the electronics power, 40% goes into cooling, 20 rest of the thing like your power consumption. So if I take so my projection is that the hyper converged data centers are not going to make sense in the long run. It is going to be distributed data centers with, rather than going after the GPUs, it will be XPUs and quantum process squids. So that's what the more likely scenario in 3 to 5 years, I would say. But in the next 3 years, it is more likely to be transmons.
Okay. Now, unless you have anything more you want to add, I want to cover more areas because I'm watching the clock. Give us a thumbnail sketch. Each one of you can cover 2, 3, 4. Then other people can pick it up. What are the application environments where quantum computing or verticals industries application environments where quantum computing is more ideal than the regular, whatever regular computing it is? Pick up. Anyone can.
Yeah, so I can jump in, and yeah, I can say that. So that's a fascinating area, right? So I would say where we are sitting here today, look like materials discovery, drug discovery, risk analysis in financial portfolios. They're all things.
Folding. Yeah.
Yeah, these are all the things that are actively being pursued for quantum. But just like
Methodology. Yeah.
Yeah, so what I would say is just like in AI, we're going to have many surprising applications for quantum down the road. And I think as so far, many of us may not even have imagined the kind of applications that will happen. And I think we'll be all pleasantly surprised as the power of the quantum computers start to come
I have a
on.
list of 15 areas we can talk about separately.
We will just have an explosion of uses, and a lot of fun is going to be there in the space in terms of unexpected benefits of these technologies. So I just keep in mind that we need to become open-minded in terms of use cases.
Yeah.
Now,
anyone?
I wrote an article recently and talked about application of quantum computing in energy sector. One of the most inefficient sector, if you want to look at it, right? Whether it is wind, whether it's solar, or whether it is the traditional oil and gas, the total inefficiency is anywhere between 35 to 40% basically year over year, right? And if you look at certain areas, where can it be? So if all of us are in that age group that we have heard that there is only oil left for 50 years, for the last 50 years. So it's a hugely problem with great uncertainty, right? And it is only based on what we do is in oil and gas industry is what is called a simulation. And of the so-called how much oil and gas is under the earth by using certain mathematical formulas. And they ignore a lot of, because compute power didn't exist, they ignored a lot of features of computational fluid dynamics as such. Now, with the availability of quantum computers, I think we could probably build a more realistic scenario as to saying what is the real, close to real, how much oil or gas do we really have. Correct. At the same time, we can actually also project how fast or how slow we should be actually tapping into it. Because now that is actually tied into how we can actually use the same space, so to say, to do carbon capture, so become carbon neutral. So if you think of it, those kind of integrated problems could be a classic case for quantum computers where meaningful output will be more appreciated as such for the humanity. Again, same thing can be talked about wind and solar as well. But these are areas of simple, what I call optimization problems. Spike already mentioned about drug discovery and all, protein folding. It's not a new thing, like people have been doing this for a long time.
But virology and epidemiology require a lot more ability. Yeah.
Exactly. It's a more of a, I think when I look at these problems, how can we look at it in a more an integrated fashion, right? So if we are talking about drug discovery, traditionally what we do is we generate one molecule, we simulate in an environment and leave it alone and saying, oh, this is a potential case. But today we can actually combine the data with proteomics, we can combine it with the data with genomics, we can combine it with drug discovery, we can combine with our EHR record. We can actually build a case study of a really integrated problem rather than saying just want to find a molecule. Right. And that is that, but of course, that is, we are not there yet, but I think that is something now at least we can think possibly to do it. Right now, even when we do drug molecule simulation, we forget the water because we can't simulate that much. So I think there's a lot of gaps there. But then I would not say it's a human problem, it's just the technology challenges.
Yeah,
But
some domains cannot be solved by regular computing, so-called regular computing, right? Only we didn't talk about quantum communications and quantum cryptography.
so the
Right?
quantum
Can
communication
anyone
Sure.
pick up?
Yeah, I can pick up.
You didn't speak much yet. Yeah.
So quantum
Get him to speak.
communication, one should look, one second. Quantum communication, we should look at couple of areas. One is where it is most important and most interesting for in nations is the quantum networks, right?
Yeah.
Both from a national level, remote fields, as well as satellite or this universe level. And that is where I think quantum communication will become really interesting, and also where capital intensity should increase very fast, very soon. I think if you saw the news last week, there was a news from the European Union. They said that they need to look at all the foreign direct investments outside Europe by the European investors because they want to protect the technology, especially when it comes to quantum communication and other areas. So I think this will change the way we start thinking of this problem. And of course, quantum communication is easy. You saw the I think there was an article in Science by Dr. Prakash, who just showed an example of quantum teleportation. So you see, things are progressing fast, and so I think we will see much more capital being invested soon.
Yeah, quantum. I just want to add another dimension also. Quantum cryptography is a double-edged sword. If you incorporate using quantum computing, another company with quantum computing can have a attack. That's a double-edged sword, both sides. And I don't know whether we have enough time to debate and discuss that. We are 48 minutes already, so.
Murthy sir, I would like to bring in two things I'm bullish about. First one is the new battery design. This is something the world is waiting for. And second one is autonomous fleet operation, because for rolling out autonomous drone fleets, there exists a greater need for large-scale quantum computing.
Yeah. Okay. Okay.
So on the quantum communication side, I would say that quantum key distribution is one of the main things, and that is based obviously on the optical communication, which is the fastest, and that also depends on what you call the uh, ability to do what you call repeaters, quantum repeaters, which are used in the communication. Now, this is for the terrestrial, non-terrestrial, as well as satellite. So you got variations of that for the key distribution, and that is based on obviously the ability to do the what you call the teleportation, etc. So I would say that there are many challenges in that, but definitely Nyquist criteria and all of those criteria for multi-layer, there is multiple baud rate, these are coming back. Again, people are going to question the same way. Is Nyquist the limit, or can we have better than that? So there will be challenges similar to what we did in the 5G era. So you do expect to have some fundamental papers which are coming out from different communities in the industry. I would say quantum communication will have major impact, especially on the signaling, like weather prediction, whatever the various carbon footprint and etc. So there is a lot skill set to develop. So it is more on the research, yet it will come out very soon, I would say.
That's where your future thinking will come in IEEE, right? Yeah.
Yes, I would say.
Yeah, and I wanted to make sure that I mentioned there are two people here in addition to Chintan, Dr. Chintan Oza and Prakash, Dr. Spike
Mhm.
Narayan, Dr. Priyadarshi as examples.
Mhm.
Induct them into and get their advisory because they are every day dealing with this IEEE forward looking, and Prakash has been involved in others, and I've done it over 4 decades and many areas. So this is what we are discussing now is going to be part of your content, guys, in the forward looking thinking. Okay, now we have about 7 or 8 minutes practically. So anything that you wanted to cover, even though I have many more, that you want to, any one of you start with Dr. Speknar, anything else that you wanted to cover that we didn't cover area
Yeah,
wise?
sure. Just briefly is every time you have a brand new area that's starting to kind of grow, people always bring in physical limits of why something cannot be done beyond a certain point.
Ah,
And I think over time we have learned that a lot of these physical limits really, even though physics says it's not possible, actually happens. And I'll give you a classic example in the semiconductor industry. For the longest time, people said you cannot image a feature that is smaller than the wavelength of light being used.
yeah,
That myth was actually trashed many decades ago, right? So all of
yeah.
these so-called limits that we hear, people should be really looking more broadly to see how we
Okay,
can go around some of these limits. And I
very
think
good.
that's going to happen in quantum over and over again going forward.
Dr. Chintan Oza, I mean, I want to make sure I'm trying to prod you to, I know your time is late, but anything you didn't get to just speak as much as you really can do. Any points that you want to make?
Yeah, sure. So I would like to make a point, in fact, couple of points, which we all as leader must endorse and be vocal about. Is first one is capacity building. We need to be vocal about, because until we build a greater pipeline of a skilled workforce, because quantum economy is going to open up a new world for all of us. The
Yeah,
convergence of multiple technology is growing at the speed of light. I mean, think of
yeah,
merging quantum plus AI plus 5G plus drone.
yeah,
Look at the kind of use cases you would have, right? So this is where there exists a greater need for introducing quantum education at undergrad level and standardizing these courses.
yeah,
Apart from
yeah,
this, there exists a good amount of skill beyond the academy, and this is where uh, I feel there is a definitive need for professional body like IEEE to come forward and
yeah,
launch a certification, which a
yeah,
person can appear in exam and qualify themselves. Because right
yeah,
now, I also know quantum kind of people are there in the system, and then that is actually not good and not healthy for the system.
yeah,
Hence, we need this capacity building exercise. We need to promote clarity at government end.
yeah,
Let us be vocal. Let us align with government. Help them build more clarity in the existing policies, uh, have more clarity about data governance,
yeah,
cross-border trade, ethics,
yeah. And
and
education is not only in the quantum computing world, as Dr. Spike Narana also mentioned, that in lots of others, non necessarily quantum core knowledge is required. There's a lot of building other things, right? Refrigeration, cooling, the energy, calculate things and so on. And surrounding quantumness being used in all the QCCC, there's lots of market products, economy will be created. And so one of the things I used to say that just for India's sake, India missed a lot of boats. For example, right? China is able to capture fast enough than anyone else that any country, including America for us, we need to jump in fast enough before it's a little late in terms of strategy. Okay. You have all 1 minute to conclude. before
Quick
they
one.
cut us off.
Yeah,
I start
Prakash
with,
here.
let me just go through the line so it's easier. Dr. Spikenard.
Sure. So I would say in the end, the quantum technology in the near term that's going to win may not necessarily be the best one. It'll be the one with the most investment in trying to do something at scale. I think building and learning is the best way. It may not be the best technology, but it'll go furthest in the near term.
Okay. Okay. I'm going to go the same route, Prakash. Dr. Priyadarshi.
Yeah, so I think quantum is coming fast, and I actually left corporate career to go back to quantum. That's for my first love, even before my wife. So I believe it.
Now I have to tell this to my girlfriend. So
There you go.
good line. Thank you. I should call her quantum dear, right? So that's good enough. Chintan, Dr. Chintanoza. Then I will go. You get to conclude. Yeah.
Yeah, so the era of competition is over. We need to build bridges so that the era of collaboration begins.
Okay.
Repetitive efforts can be avoided because we need quantum to save the planet. And it is a really essential, powerful tool which can help us achieve lot many targets, maybe right from new design for aerodynamic vehicles to aviation to mobility to healthcare to whatnot. So there is a definitive new era, and that is where I seek everyone's support to begin the era of collaboration.
Prakash, you need to learn saying to your wife, I love you more than quantum. So continue.
So
You get to conclude.
yeah, so the conclusion is very simple. The winner, as Dr. Spike said, will be the one who has the highest investment and can reduce the error and scale, and that appears to be more likely in near term. Like our x86 one over Motorola, I would say similarly, I would expect that the transmon computing will overtake. That is
Okay.
what I see. But
Okay.
at the level of national level, like National Quantum Mission in India, definitely you see lot of what you call spread around startups, which some of them may surprise, and we expect that such things will happen all over, whether it's in UK or US
I
or
need to
EU
start
or
concluding now.
China.
Prakash, the
Yep.
time it, otherwise they'll cut me off.
Yeah,
It's happened before.
thank you.
So
I'm done.
thank you a lot for all of you to have pitched in. This is basically national strategy, technology strategy, industry strategy that you all contributed together. I was the Sarathi, like what Dr. Priyadarshi has behind him, to do all the good work. He has this Krishna and Arjuna's thing, the chariot that he has. So thank you a lot,
Thank you.
and we appreciate your time, your ingeniousness, and your creativity, and your maturity in the industry. Thank you,
Nice
Dr.
meeting all of
Prakash
us.
Narayan, Prakash Narayan, Dr. Priyadarshi, Satyam Priyadarshi, Dr. Chintanozad, and my long-term friend Prakash Ramachandran.
Thank you very much.
You need
for the
more time
opportunity.
next time, okay?